So today's topic is Introduction to Mealy machine. So Mealy machine, as you know, it is the finite automata, uh, or you can say finite state machine that can generate the output. So finite automata, as you all know, it is a mathematical model of finite state machine. And NFA and DFA are their types. And finite automata, as you all know, it works as a language acceptor, because when you are giving a input, some string as an input, and when you will read the entire string, if you are at final state, then we'll say that string is accepted by finite automata. So likewise it will do with all the different strings, and that is the reason, and it will do with many strings, and few of them it will accept, few it will not accept. So that is the reason finite automata, it is called as a language acceptor. But it will only, either if you are on a final state, it means the string is accepted, but there is no output. Output will not get generated. So when the output is attached with the finite automata, then we got two types of machine. First is Murray machine, and second is a Mealy machine. So the So the formal definition of Murray machine, you can see here in front of your screen. It is denoted with the help of six tuples. So here your Q, then second capital Q, which is you know that it is a set of states. Then sigma, then Q0, then your delta. It all has the same meaning as the previous. So Q, you know, it is a set of states, is a finite set of states. Then sigma, you know that it is a collection of input symbols. Then delta, here it is capital delta is used here to denote the output alphabet. So this capital delta, it holds the symbols. It is a collection of symbols that you will be using to generate or to show the output. So that is the reason here it is capital delta. It is new thing which is added. Then small delta, it is, the meaning is same as the previous finite automata. So small delta, it is nothing but the state transition function. And again, it maps your current state of finite automata and the input symbol which that current state will accept. And depending upon this two, it will move to the next state. So that is the reason it is shown, the mapping is shown here in this way. Q0, it is nothing but the initial state. And here you have lambda, it is your machine function. So machine function, you know, the state and the output which it will generate. So that is shown here with the MA. Now here you can see the difference. This is your Murray machine. So here it's machine function, right? Lambda, how it is shown, you can see the capital Q, that is here, this capital Q is nothing but a set of states, and it is directly mapping with the output symbol delta, right? It means what? For each state, there is some output symbol associated, right? Murray. So here it is, you can remember the, two O's. It means output on state. You can say like that, output on state. So irrespective of input symbol given as a input to the state, the output is generated. So you can give any input to the state, but its output is fixed. So here you can observe that from the first transition graph, for state Q0 output is 0, and for state Q1 output is 1. And same thing is shown here in the MAF, here you have states. So Q0, Q1, output symbols are 0 and 1. So output of Q0 is 0 and output of Q1 is 1. And after giving this input A, B, A, B, B, so you got this output, right? I'll explain this output after explaining the output of Mealy machine. So now here in the Mealy machine, you can see that the MAF, that is machine function, it is it depends upon the current state and the input symbol which you are giving. So depending upon uh, which input symbol the current state is accepting, the output will be generated. So the input symbol plays important role in placing in generating the output, whereas in case of Moore machine, the input symbol plays no role in generating the output. So here from this MAF, you could see that when Q0 state will accept input, uh, here you can see when Q0 will accept input symbol A, it generates output 1. So here, this part you can see here, above this slash is the input symbol and after the slash is the output symbol. So Q0 on accepting input A, you will be getting output 1. Q0 on accepting input B, it will generate output 0. Now Q1 on accepting input A, it will generate output 0, and Q1 on input B, it will generate output 1. So same thing is shown in this MAF table. Now we'll just check this, how it generates the output. So the input string is A, B, A, B, B. So obviously the very first symbol will be given as an input to your initial state, which is Q0. So Q0 will accept the first symbol because as we will be traversing the input string from left to right. So first symbol from the input string will be read by the initial state Q0. So Q0, when it will accept input A, it generates output 1. So here you could see the output is 1. Then on B, on input symbol B, Q0 will not only traverse to Q1, but it will also generate output 0. So for input symbol B, the output generated by Q0 is 0. Now you are on Q1. So Q1 on accepting input A, the next input symbol after B is A. So definitely currently you are on Q1. So Q1 on accepting input A, it will generate output 0. Here you can see. So on accepting this third symbol, it will generate 0. Then and it will traverse to Q0. Then Q0 on accepting A, it will generate in output 1. Then Q0 on input symbol B, it will generate output 0 and it will traverse to Q1. Then Q1 on accepting B as an input, it will generate output 1. So that is the reason you got it, you got this output. Now, if you observe here, now we will see the almost, if you compare Mealy machine, the transitions are the same on inputs, on different inputs A and B, they are transiting on the same. So that way both the machines are same. But now if you'll observe the output, this part, and just check how it generates the output. Now because initially you are on Q0 state, so as Moore machine, it the output generated by the state is not dependent on the input symbol. So once you get entered on the state Q0, so Q0 may accept the input or it may not accept the input, it will generate output 0. So that is the reason you got the first 0 here on Q0. Then it has accepted the first input symbol A, then that is the reason it has generated output 0. Then Q0 on getting input B, it is traveling to Q1, and as you will reach to Q1, immediately the output 1 will be generated. Okay, then on receiving input A, immediately you are reaching to Q0. So output 0 is generated. Again on next input A, it will generate another output 0. Then on B, immediately it will go to Q1 and it will generate 1. And on another B, again it will generate 1. So this is how the output will be generated, and that is the reason you are getting here extra 0, the first extra 0 you will get here. So this is how the output will be generated, and this is the difference between the Moore and Mealy machine. Okay, so now in this lecture we will be discussing the Moore machine. So you know that finite automata with output. So we have two types, Moore machine and the Mealy machine. So this is the formal definition of Moore machine. You know that here it consists of 6 tuples. Here this x is nothing but your capital delta. The same thing I have written here. So this is your capital delta. So Q, sigma, these are all, the meaning is same as the earlier, the finite set of states, and sigma, it is nothing but the output. It is input alphabet. O, it is used as a finite set of symbols. Then this small delta, it is your state transition function. Capital delta, it is your output transition function. And Q0 is your initial state. So I want you all to take a note of this, all the 6 tuples. So now here in this example, we have to construct a Moore machine to find out residue modulo 3 for binary number. So residue modulo 3 is, it means when you will try to divide a binary number by 3, then your Moore machine should tell what is the remainder. Okay. So for that, consider this logic. So assume that we have I as a binary number. So if you add 0 after I, so what you will get when once you will add 0 after I, you will get I 0, I dot 0. So when you will add 0 after I, any binary number, after I is any binary number, after I, when you will add 0, its value become 2I. It means it becomes double. For example, if you have 1 as your binary number, and if you will add 0, you will get 10. That is equal to 2, which is decimal equivalent. So binary 1, it is decimal equivalent is also 1. When you will add 0, you will get 2, which is your decimal number.